Hello everyone. Uh, so I'm recording this class because actually I missed the September 14th class because of some personal reason. So I promised I record the day two class of this storage system class course. So uh, so I will record this class. Uh, Actually, this class is about the introduction to storage system. So in this class, I will cover some basic concept of the storage system as a perspective of the operating system or other some communications and or IO device, I input and output controls. So actually, in this course, we will learn about the storage system and we will focus on the solid state drive because uh, solid state drive has the flash memory, and the flash memory is faster than the hard disk drive, like because the hard disk drive is the kind of a mechanical drive, so mechanical storage system, but flash memory is a kind of semiconductor devices. So if we use the mechanical drive, the like hard disk drive, then we need to seek the location of the target data. But so that means we need seek time for the target data. But if we use some semiconductor devices such as the memory devices like DRAM or flash memory, then this type of the memory has the fixed latency. So nearly fixed, not not constant always, but it's the constant latency. So actually the performance of the flash memory is higher than the performance of this magnetic drives. So that's why we are focusing on the solid state drive. But people diving into the world of the solid state drive, I think we first need to understand how the storage system work in the conventional computer systems. Also, we need to know how this conventional storage system is controlled by operating system or some computer systems. So this is the second class of this course, because the first day we just introduced about I just introduced about the entire course, that like this storage system course. And then in this time, I will cover some basic concept of the storage system control in the computer system. Okay, so in this time, I will focus on some IO device control by operating systems. Okay, let's start. So this is the recorded uh, class. So it's not, it's not easy, but of course it's not a real-time class. So I just uh, need to keep. I just need to keep saying uh, in front of the camera. It's not easy, but yeah. Okay, let's start. Uh, so in the today's class, we will focus on some basic concept of the storage device and then how this operating system controls these storage devices. Also, we will cover the property of the hard disk drive. So because actually the hard disk drive is the widely used storage devices because the data density of the hard disk drive is much higher than the density of the main memory, like DRAM. Also, the price, that means the cost of the hard disk drive is much lower than the price of the DRAM. That's why the hard disk drive is widely used as the main storage devices in the computer system. Also, hard disk drive is the non-volatile memory. So that means that even though the power is turned off in the computer systems, the data stored in the hard disk drive is not erased. And that's why we use the hard disk drive as the main storage devices in the computer system. But what's the drawback of this hard disk drive? The disadvantage is that hard disk drive is very, very slow. It's much slower than the slower than the DRAM. That means that the performance is very low. So if the data is accessed from this hard disk drive, it will take a very long time. So if the data is frequently accessed from the hard disk drive, then overall execution time of this application will be very long. So that means the performance will be very low. So this time we will learn how operating system control the input and output devices, because a conventional storage system like hard disk drive is also communicate with the CPU via some IO input and output communication media such as SATA or IDE. So we will cover the input and output devices and then hard disk drive, and then we will cover the file system in the next class, not today. So in today's class, we will cover the IO devices and how the operating system controls IO devices. I think I need to use this pen, and then we will study the characteristics of hard disk drive, and then how the data is accessed from this hard disk drive, and then how operating system also control the hard disk drive. Okay, so the two main topics of the today's class. Okay, so let's start from the terminology persistence. So actually in the previous class, I recommend you to read the chapter 30 to 35, and I don't remember, but if you read this textbook, the 3 steps of the operating system, then you can find that the first chapter is just to mention the terminology persistence. So what does persistence mean in the computer system? So if you do not know the meaning of some terminology, then you can find the dictionary. So, but we have Google, so we can search the meaning of the terminology by searching Google. Okay, so if we search the meaning of the persistence, terminology persistence in Google, then you can find the definition like this. So Google used the Oxford Language Dictionary. So this is the definition by Oxford Languages. Okay. So what is the definition? the persistence, the definition is firm and obstinate continuance in a course of action in spite of difficulty or opposition. So that means so its meaning is somewhat, sometimes it's a negative or sometimes it's positive. But as you can see, the meaning has some kind of negative meaning, such as the stubborn or obstinate. But in spite of a difficulty or opposition, but that's the some normal meaning of the persistence. But we are computer science, we are learning computer science and then computer engineering, then we need to know the terminology persistence in computer science or computer engineering. Okay, because the obstinate is the somewhat the firm and stubborn, or it's that kind of hard-minded. Okay, then what's the meaning of the persistence? So actually, the textbook has the very funny textbook provides the very funny conversations to explain the meaning of the terminology persistence. So in this conversation, the student asked the meaning of the persistence to professor. So persistence. So and then the main meaning of this word persistence is a firm or obstinate continuous. So it's the same. Okay. So I think the professor also searched the Google. So actually the main meaning of this persistence is the firm or obstinate. But in the computer science or computer systems, what does persistence mean? We frequently use the persistence memory or persistence in computer systems, in the computer systems. What does that mean? Okay, so you can find the meaning of the persistence here. So to make the pitch persist, the persistence means that it is applied to the information. The persistence means that making information persist. So that means that even though the computer is powered off, or the computer crashes, or some failures happen in the computer systems, then the data is still stored or still can be recovered. So the making information persist, that means that despite computer crashes, disk failures, or power outage, then in this some abnormal situations, the data stored in the computer system is maintained or can be recovered. That is the meaning of persistence. Okay. So what's that mean? So that means data is persistent. So that means that data is stored, and then this stored data. So data can be also stored in the main memory like DRAM, but we already know that if we turn off the power of this computer system, the data stored in the DRAM is erased. So it's removed because DRAM is the volatile memory. But what does persistence mean? So in order to keep this data in the computer system, then we use the storage devices. Then even though the power of this computer system is off, then data in the storage system is maintained, is kept. And then when we turn on the power of the computer system, then we can recover the data from these storage devices. That is the meaning of persistence. And then sometimes because of this, sometimes the storage devices are called the persistent memory. But the meaning of the persistent memory is somewhat different from the storage devices, but we can say that the storage devices are the kind of persistence memory because the data stored in this type of memory can be recovered after power failures or power crashes, some power outages. Okay. So data is kept or maintained in the storage devices or memory. That is the meaning of the persistence. Okay. So also I copied the meaning of the persistence from Wikipedia. So in the computer science, persistence refers to the characteristics of state. Okay, it's just state or the state can be recovered, what data can be recovered from some failures or power outage. Okay, that outlives the process that created it. So this is achieved in practice by storing the state. So what does state mean in computer system? The state means that just a data. Okay, so when we mention the state of the architecture, that means that the data is the state in okay, I don't know why it doesn't work. Okay. Oh, I don't know. The eraser doesn't work. Okay. If we mention the state in computer architecture, then that means that state means the data in register file or main memory. Okay. So if the instructions are executed in the computer processor, then the data is updated in the register file, like the R-type instruction by R-type instructions, or the data is also updated to the main memory by store instruction. Okay, data or data transfer instructions. So that means that if the instructions are executed in the computer processor, the data in register file or main memories are updated. So that is so that means that the state of architecture is changed, or state of architecture is updated. Okay, and then if the state is persistence, that means that we need to store this data to the more reliable memory space or some storage space. Okay, and then if the failure happens or some like a power failures or some crashes can happen in the computer system, then the state of this architecture is the architectural state is changed or corrupted, okay, or removed, so erased. So in that case, we need to recover this state. So this is the original state. When the computer system recovers from the failures, then we need to recover this state from the some persistent memory or storage devices. So when we mention the persistence in the computer system, then that means that we need to store the state or data, that means the data in the computer data storage or persistent memory. So then the systems are recovered from the failures or crashes, then this state can be recovered from this storage. So that means the persistence in computer systems or computer engineering or computer science. Okay, and then in order to support this persistence in of the computer system, we have storage devices. So storage devices is the number of memory. So that means that even though the power is off, then the data stored in this number of memory is maintained. And then that means that if the computer system crashes or failures happen, then we can recover this data from the storage devices. And then in order to support this function, then the application need to store or store their data or state to the persistent memory or storage devices. Okay, so persistence. So actually we usually so we usually use our storage devices very naturally. That means that we do not consider about the persistence of our computer system. We just store our data to the storage devices or hard disk drive, and then as a file, right? But why? If we do not save our work, if we do not save our word process document or PowerPoint slides, then if the power failure happens in our computer system, then our work, our progressing work or some document is removed from our computer systems. So save our document, saving our slides in the storage device means that we make this data persistent. Okay, we make our data persistent in our computer system. And then for this persistence, the storage devices are used in the computer systems. Okay. Okay. So also the storage is included in the memory hierarchy. So this is very popular, actually the basic of the computer architecture. So if you study the computer architecture course, then you can understand the memory hierarchy. In the memory hierarchy, in the higher level, this memory is the cost is high, but performance is high, the capacity is very low because the cost is high, performance is high, cost is very low because we do not have perfect memory. If the memory cost performance is very high, then it's very expensive. So that the density is low. So we use this very fast memory as the register file, and the register file is closest to the processing engines, like actually core, like execution engines. Okay, execution units. So these processing engines or execution units frequently access the data in the register file very quickly. And then if the data can be accessed very quickly, then we can improve the overall performance of these computer systems. That's why the frequently used data is stored in the register file or higher level memory. Also cache. Cache is located inside of the CPU chip. Okay, fine. So and then cache memory also has the SRAM cell. So we already know that SRAM cell is very fast and very expensive, and then the density is low. So that means that the performance of the SRAM is very high. So that's why we use the SRAM as the basic cell of these cache memories. And then also the size of the cache memory is small. So smaller compared to the main memory and then storage. And the main memory. So the performance of the main memory. So for the main memory, we use the DRAM, the dynamic RAM, for the main memory. And then we already know that the performance of the DRAM is lower than the performance of SRAM. That means that the latency is longer, it's higher, latency is higher. So it's slower than cache memories. But the cost is lower than the SRAM, and then the density is higher, but it's still expensive. And then on the lower level of this memory hierarchy, we can find the storage. Okay, and then we already know that the DRAM is the volatile. That means that the data stored in the DRAM is removed if the power is on off. Power is off for the DRAM. How about the storage? The cost, the storage cost, the storage is cheap, like SSD or hard disk drive. Then the performance is very, very low compared to DRAM. Okay. And then capacity, but capacity is very high. And then another feature of this unique feature of this storage device is that the storage device is the non-volatile memory. So the data is not erased even if the power is off. So that means that this is the persistent memory. Okay. So this is the conventional memory hierarchy in our computer systems. So why do you use the memory hierarchy? Because we can exploit the locality found in the application. That means data locality. So data locality means that if the data is accessed, then the same data can be accessed in the near future, or the neighbor data can be accessed. That is the locality. And then in order to exploit this locality, then we build the memory hierarchy. So then this small memory is located close to the processors, and then the performance of this small memory is very high. But due to its cost, we cannot use the large memory for this register file or high-level cache as a level caches. But for the lower level memory, like a storage or DRAM, So density is very high, but that means that cost is low, but the performance is also low. So that's why we locate this storage in the very low level of the memory hierarchy. Okay. Also, we already know that. So usually the hardware, the computer processor manage the register file and cache, and then until the main memory. Okay, but the data in the storage is managed by operating system. Okay. Also the usually the main memory is also managed, can be managed by operating system, but it is also or managed by hardware, that means the processor, the computer processor. But about the storage is connected to the main processor like CPU via communication link, such as the storage interfaces and the data communication between the CPU and storage devices are managed by operating systems. Okay. So it looks like this. This is the CPU. And then via this storage interfaces such as SATA or PCIe, the storage devices are connected to the CPU. And then the data communication between CPU and storages are managed by operating system. Okay, that means the software. Okay. So usually the conventionally the storage system is some area of the operating system, but recently the criticality of the storage system is it's increasing recently because the computer system handles the very large size of the data, so the big data, called big data. So the performance of the storage system or these I/O devices are very critical in the entire computer systems. That's why we are focusing on the storage system, even though we are computer architects, we learned about the computer architecture. So recently the computer architects or computer architecture communities also focus on the storage architecture or storage systems. That's why we are learning about the storage system in this course. Okay. Okay. Then before diving into the world of the storage devices, let's learn about how operating system controls the I/O devices. That means the input and output devices. So what is the input and output devices in the computer systems? So like keyboard, mice, some other. So these are the input devices, and then so also the network, like the Ethernet, is the input and output devices because the data is given to the CPU via these devices like keyboard and mice. Also, the data is communicated with data is the key. So the computers are communicated via network interface card like Ethernet device, Ethernet card, the network interface cards. So these are the I/O devices. So if we see the main board of the computer system, then we can find that, oh, this processor is connected to many different type of I/O devices, right? So this is the photo of the very old mainboard. Okay, so because this mainboard has the AGP slot, so So older generation GPU slot. And then as you can see, this is the CPU socket. And then here is the DIMMs. Also, the CPUs are connected to the main memory like DIMMs via this CPU and DRAM bus. And then, except this, also, if you see this main board, you can find that this main board has many peripherals. That means the many different types of I/O devices. So you can find that, oh, this is the SATA port. And then you can find, oh, this is the PCI slot. So you can find the I/O port for the keyboard and mice. There's a serial connector, and you can find so many I/O devices, I/O port in the computer system. So actually, in the entire computer system, this processor is connected to many different kinds of I/O devices via this some interconnection network, or called the some communication channels. Okay, and then let's see how the CPUs are connected to the different I/O devices. So this is the overview of the computer system architecture, and then but this is an old generation of the computer system architecture. So as you can see, the CPU is connected to the memory, some main memory like DRAM. So CPU is connected to graphics processor like GPU, and then also CPU is connected to the many different peripherals like I/O devices. That means I/O devices. So can you find in this diagram, in this figure? So this figure shows the topology of the old computer system architecture. Can you find? At first, we can find that the CPU is connected to many different kinds of devices, and we can find hierarchy between different type of devices. Why? Because of performance of these different type of devices. What does that mean? So actually, the CPU is connected to main memory and GPU and then other peripherals. But as you can see, this memory bus is very wide, and then it supports the the high data bandwidth. Why? Because the large amount of data is given and communicate between CPU and main memory. That's why this memory bus is very wide, and it supports the high bandwidth. How about the GPU? So the GPU also requires the very high bandwidth from the CPU or in the computer system. But in the older generation computer systems, actually the GPU requires some lower data bandwidth compared to the main memory. So that's why the GPU is connected to some specific port like called the AGP, or recently we used the PCIe. But this bandwidth of this AGP or PCIe and the connection is lower than this main memory bus. Okay, so it is because the performance of a GPU is lower than the performance of the memory. So that means in the slide, the performance means the data bandwidth of what these peripherals like storages. So in the old computer system, we use the storages interface such as the SCSI or SATA. Then, as you know, the bandwidth of the SCSI and SATA is much lower than the memory bandwidth because the performance of the storage system is very, very low. So if the data is read from this storage system, but the storage system is very slow, so we don't need the high bandwidth bus for the storage devices. Also, as you can see, these storage devices are connected to the same interconnection. It's a some common bus, common interconnection bus. So that means the resources for this common interconnection bus is low compared to this memory bus, the high bandwidth memory bus. That means the cost is very low because the storage system is slow. And then the CPU, what is memory, access this storage system with the low bandwidth. Okay, that's why the old computer system has like something like this topology between the CPU and IO devices. And recently, the computer this computer system architecture is also changed because and then this figure shows the modern computer system architecture. Okay, so in this architecture, the CPU is directly connected to the memory, so it's obvious because the modern computer system also requires the very high bandwidth data bandwidth between CPU and main memory. It's critical for the performance of an entire computer system. So we also require the high bandwidth between CPU and memory. And how about the GPU? And then recently, the GPU used the PCIe interface, and the PCIe interface also supports the very high bandwidth. But recently, the GPUs are directly connected to CPU. So in the old architecture, the CPU is connected to GPU via the general I/O bus like PCI and or AGP. But in the modern architecture, the CPU is directly connected to the GPUs is directly connected to CPU via PCIe interface. It is because GPU also requires the very high bandwidth. Okay, and then the Intel architecture, the CPU is connected to I/O chip like is actually in the old architecture it is called the Southbridge chip. Then actually the memory is controlled by this bus is oops what happened this what happened I don't know. So I think this PDF is working. Okay. The old architecture, the CPU and memory is connected via Northbridge chip, and then this Other peripherals are connected via South Bridge chip. And then but in the modern architecture, this North Bridge chip functions are integrated in the CPU chips. Okay, so CPU chip include the memory controller or graphics interface. So the node bridge functions are integrated in the CPU chip. And then the CPU and I/O chips are connected via DMI in the Intel architecture. It's a direct media interface. And then in the SAS bridge chip, each I/O devices are connected point to point. Okay, so network devices can be connected via PCI bus, and then storage devices are connected via SATA channel or serial ATA SATA. Also, the very slow devices such as keyboard and mice are connected to these I/O chips via USB interfaces. Okay, this is the modern architecture. And then this slide shows the Intel Z390 chipset block diagram. Then also, as you can see, this block diagram shows the modern computer system architecture. As you can see, this is the CPU, and there's this graphic card GPU are directly connected to the CPU. Also, the memory DIMMs are connected to the CPU via DRAM memory controller. So as you can see, DRAM between the data bus between CPU and DRAMs are supports the very high bandwidth. Then the CPU and this mainboard chipset, this I/O chipset, is connected via DMI, so Intel's direct media interface, maybe DMI. And then as you can see, the many I/O devices are connected point to point. Okay, so SATA and then USB and then PCI buses are connected to this Intel mainboard chipset. But as you can see, SSD. So storage devices can be also directly connected to the CPU, because recently the data communication between storage to actually this high speed storage like SSD or Intel Optane storage. So this high performance storage is performance is very high, and then we need the very high bandwidth between CPU and storage. So sometimes this Intel SSD or Optane SSD can be directly connected to the CPU. Okay. But just understand that this is some modern computer system architecture. Okay, how the CPUs, GPUs, or memories are connected, and how the other I/O devices are connected via I/O chips or mainboard chips in the computer system architecture. Okay. Okay. Now let's see how the CPU communicates with the typical I/O devices. So if you see some I/O devices such as the storage devices or some other hardware such as keyboard and mice and one network interface card, then you can find that it's some typical architecture of the I/O devices. So I/O devices are composed of interface part. This is some hardware part, and then also the I/O devices has its own system like microcontroller and memories or other hardware chips or hardware devices. So actually these IO devices can be connected via this interface, and then this interface has some registers, and then through these registers, the CPU, that means operating system, can control the IO devices. Okay, so this is called the interface part. And then inside of this IO devices, this is also system or some independent system. So IO devices can have the processor or microcontroller, like, or CPU or even CPU, and then this IO device can run the software, and this software is called the firmware. Okay, system firmware. So in order to run this system software, then this IO device may have the memory like DRAM or SRAM, or like even also the IO device may have some other hardware specific chips or hardware specific devices. So this is some typical structure of the IO devices. So as you can see, IO devices are composed of the interface part, and in the interface part includes some registers that represent that shows the status of the IO devices, also receives command from the GPU or operating system, also some buffers for some data communications. Also, the IO device has the internal parts. The internal part has its own system, and then this internal part may have the microcontroller or even its own memory system or some specific chips. So for example, we can see the solid state drive. So this slide shows the figure of the Intel SATA SSD. So as you can see, this SATA SSD has the interface part. So through this SATA interface, this SSD is connected to the CPU or entire computer system. So through this SATA interface, the SSD may receive the command. Also, SSD also transport its own status to the CPU, and then SSD receives the command from the CPU, that means the operating system. Also, SSD receive the data or transport data to the CPU. So this is some interface part, so hardware part. And then inside of the SSD, we can find the SSD processor. So we usually ARM processor or real-time ARM processor as the SSD processor. And then SSD may have the DRAM. So, and then SSD also has the NAND flash memory. So this is NAND flash memory is used as the main storage media inside of the SSD. Also, this is the ARM processor. So ARM processor can run software, that is the firmware of the SSD. Then in order to run this firmware, SSD has its memory system like DRAM or SRAM. So it's a cache memory here. Also, this processor, the SSD processor, manages NAND flash memory. Okay, so this is its own system of the IO devices IO device, and then this IO device communicates with CPU via this interface. So this is the typical architecture of IO device. Okay, so that's how this IO device is communicate with the main computer system, like host computer system. So this is the CPU, and then as we already see, so this CPU is connected to the I/O devices. So we frequently call this CPU is the host system. Then this I/O device is just the I/O device. Okay. So this I/O device need to communicate with the host system. Okay, CPU, and then actually this is the operating system runs on the CPU, and the operating system control this I/O devices. Okay, so and in order to control this I/O device, we need to set the protocol. So protocol is some promise for communication. Okay, so and then this protocol is also defined, and then based on this defined protocol, the operating system delivers command to the I/O devices. Okay, so this is some typical protocol of the I/O protocol for I/O devices. Like just wait, was check the status of the I/O device, and then wait, and then write some command or data to the register inside of the I/O device. Also, or write command to the some command device, command register, and then wait, and then check the status of the I/O device, and then wait until this command completes in the I/O device. Okay. And then when the CPU control the I/O device, we can use the two different control method, like polling type method or interrupt type method. So I believe most of students know about the polling and interrupt type. So what is the polling? So when the CPU gives the request to the I/O device, then the CPU need to wait until the response comes from the I/O device. So that means that the response when but the I/O device is very slow compared to the CPU, then CPU need to until the response comes from I/O device. Okay. So how can the CPU knows the I/O device completes each request? Okay. The first method is polling. The polling means that the CPU continuously check the status of the I/O device, like so by reading some status registers, the CPU can check the status of I/O device. So, and then the second method is the interrupt-based control. So interrupt-based control means that the CPU after CPU gives the request to the I/O device, then CPU wait. So the interrupt is given from this I/O device when the request is serviced by I/O device. Request is done by I/O device. Then the interrupt is raised, then CPU can continue its previous task. So that is the interrupt-based control. So the polling based control, the CPU is executing its own job and then give request to the some IO device such as disk, like hard disk drive. Then the hard disk drive process the request from the CPU, and then CPU continuously check the status of the hard disk drive. And then if the request is serviced by hard disk drive, then the status is changed, and then CPU receives the data from the hard disk drive and then continues its own task. This is the polling based control. And the interrupt based control, the CPU raise the interrupt and then give the request to the hard disk drive. Then CPU waits until the interrupt is raised by hard disk drive. So CPU does not care the status of this hard disk drive. Instead, CPU waits. CPU continues its own task when the interrupt is raised by this hard disk drive, and then the data is delivered to the CPU. Then CPU can resume its own job, like this task. So while the hard disk drive or some other IO device process the request from the CPU, then CPU can execute the different task or different thread, okay, by context switch. So this is the interrupt-based control. So what is the benefit of this interrupt-based control? So while the request is being processed by the IO devices such as hard disk drive, the CPU can execute the different task. Okay, that is the benefit of the interrupt-based control. And then the CPU the CPU does not need to check the status of the IO devices. Okay, so actually for this polling-based control, the CPU needs to continuously check the status of the IO devices. So that means that the CPU resources are wasted checking the status of the other IO devices. So that is the disadvantage of the polling-based control. But for the interrupt-based control, the CPU raises the interrupt and then gives the request to the other IO devices, and then CPU can execute the different task by context switch. This is so CPU's resource is not wasted with the interrupt-based control. So, but interrupt-based control always better. It's not, no. So, if the IO device is very slow, so that means that this time will be very long. So this processing time by IO device will be very long. So that means that IO device is very slow. Then interrupt-based control is better than the polling-based control. But if the I/O device is very fast, the performance is very good, very high, then this time will be very short. That means the processing time by I/O devices. So what's the disadvantage? So this context switch is very uh, context switch is the very is a is a the very heavy performance burden in the CPU. It's very it's not easy. So it's not simple. So this is the very heavy performance burden to the CPU. So if the context switch is frequently happens, then the performance is significantly degraded. So if the I/O device is very fast, then context switch will happen very frequently if we use the interrupt-based control. So that means the CPU performance will be very degrade. Is the performance overhead by this interrupt-based control will be very high. Okay. So if device completes a task very quickly, the interrupt-based control is not good. So but sometimes we don't know when the request is done by these I/O devices. So the speed of the device is unknown. We can use the hybrid approach. So that means that firstly, we just check the status of the I/O devices using the polling-based control, and then we just switch it to the interrupt-based control. Okay. So frequent interrupt is not good. Okay, because it will cause very frequent context switch, which will be, and this context switch is the very heavy burden to the CPU. Then we can use some another technique, because if the data transfers are directly controlled by CPU, that means that the CPU's resources are also used for this data transfers. And then, but data transfer is a very simple job. So actually the data transfers can be done by its on dedicated hardware. And then this process is called the direct memory access, called the DMA. So DMA means that actually the data, when the data transfer happens in between host and I/O devices, then this data is actually the data is transferred between the main memory and then the memory inside of the I/O devices. So this is just the data transfer. Okay, and then CPU is involved with this data transfer, then CPU's resources are wasted for this data transfer. And then usually, as I mentioned, the interfaces between the CPU and I/O devices support the very low data bandwidth. That means that the performance is also low. And if the data transfer is controlled by CPU, and then the CPU's resources are occupied by these data transfers, it is not efficient. So we can use the direct memory access, because the data access are just done between the direct main memory and then the memory inside of the I/O device. So this data transfers can be controlled by dedicated hardware or dedicated protocol called the direct memory access, DMA. So with this DMA, we can also reduce the performance overhead by data transfers. Okay, because the CPU resources are not wasted by these data transfers. Okay. So if DMA is not used, then the data transfers is controlled by CPU, and then these CPU resources are wasted during this data transfer period. Okay. But the DMA is used, then the data transfers are controlled by dedicated hardware and dedicated protocol. Then during this data transfer, we can use the CPU resources for different tasks. Okay. Also, there are two different communication methods. Is a programmed I/O called the PIO and memory mapped I/O. So it is called the MMIO. So programmed I/O means that also this data transfers between the CPU and I/O devices are controlled by CPU instructions. That is the programmed I/O. So that means the CPU involves in these data transfers, and then CPU also supports some dedicated instructions that control the data transfers between CPU and I/O devices. Okay, this is the programmed I/O. Oh, I don't know what happened, but recently we used the memory mapped I/O, because in order to support the programmed I/O, the CPU resources are also wasted, because the CPU need to support its own instructions that supports this programmed I/O. So that means the CPU directly access some memories like or registers inside of the I/O devices via using its dedicated instructions like in and out instructions. Then in order to support this instruction, the CPU resources are also wasted, required. Okay, but if the memory mapped I/O is applied, the memory space of that means the register or some dedicated register inside of the I/O device or some memory space inside of the I/O devices are handled like some normal memory space in the computer systems. So if the data transfers are handled by this this memory space or some memory mapped I/O, then the CPU can use the normal data transfer instructions like load and store. Okay. What is the benefit of the load and store instructions? Okay. What is the benefit? So let's think about how load and store instructions are executed inside of the CPU. Okay, CPU. If the load instruction is executed, then the execution of this load instruction is controlled by hardware, entirely hardware. Right. So load instruction is executed inside of the CPU, like core, and then if the data is not found in the L1, then we need to access the L2. Sorry, we need to access the TLB and then access the L1. Its data is not found. Need to access TLB and then access the L2. It's not found. L3, then main memory. So these memory instructions are automatically done by hardware. So we can just execute the load instruction or store instruction. And then Because all overall operation is controlled by hardware. So this is it's just simpler than the programmed I/O. So in order to support the programmed I/O, the CPU requires the dedicated instruction that access the other I/O devices. But with the memory mapped I/O, we just need the load and store instructions, and then this memory space, like of the I/O devices, are included in the entire memory space of the computer systems. Okay. So recently we use the memory mapped I/O as well. Okay. Okay. And then but controlling the I/O devices is not a not an easy job. So it's not an easy task because the CPU actually we can use the various types of I/O devices. There's many different I/O devices. So if there are many different I/O devices, and then actually that means that these I/O devices are entirely different. So then what's the problem? So in order to control these different devices, then we need the different interfaces for some different control. Okay, it will be very complex. So how can we simplify these different type of I/O devices or different type of layers? We can use the abstraction. Okay. So if we use the abstraction, then the higher level need to just understand some very simplified interface. Okay, we can just understand the simplified interface in this higher level, and then the lower level is controlled by some interface signals between comes from this higher level. Okay, so actually this is the storage devices, and then actually the data management inside of the storage device, and then how the data transfer in between this storage device can be very complex. It's not simple, right? So actually it's not simple. So we learn about how the data is managed inside of a storage in this course, okay? But it's not simple. But also there are different types of storage like SSD, hard disk drive, also the hard disk drive by Seagate, Western Digital, and the SSD by MSC. SSD then use the MSC flash memory, and the SLC, or even the QSC flash memory. So actually there are different types of devices or storage devices, or some different type of I/O devices. It's not easy to control this different type of devices. Okay, so how can we control this different type of device? We can use the abstraction. So the higher level, this higher level just support the very simple commands or very simple interfaces. So for example, this is the application. How can we access the data inside of the storage devices? So think about this. So how can we access the data stored in the storage device. In a C, in a C program, we just define the file pointer to the some file. So we just define the file pointer, and then using this file pointer, we open this file, right? And we read the data inside of this file. Then the data is transferred to the main memory of the system. And then using this data, then we can process the data that's stored in the main memory. And then if the processing is done, we close this file and then release the file point. That's how the data is handled by application. Why? So which command is supported? Open, read, write, close. It's very simple commands. And then these simple commands work on the top of a file system. Okay, because the files are managed by file system, by operating system. So the file is pointed by file pointer, then we can access this data inside of the file, and then also we can update this file using this write command. Sometimes we can directly access the data on the storage. Now this low-level access is also supported for data management on the storage devices. Okay, we can use the file system. We can access the data to this file system, or we can directly access the data on this data inside of a storage system. Also, this data read, write, erase is controlled by block read, write. So we don't know how the data is managed inside of the storage system. So we will learn about the detailed management of the storage system in the next class. But we don't know. No, operating system just manages the data on the storage system with the block read, write, erase command. Okay, so block like a 4 kilobyte block or something like 8 kilobyte block, the operating system just managed this block. Okay, and then read block, read and the write block. So operating system just generate the read block, write block, or some erase block command, and that's it. It's very, very simple. The inside of the storage system can be very complex because our system is usually our system is very complex, but operating system just generate the very simple command: read, write, and erase is a block-based read, block-based write, block-based erase command. That's it. And then how these commands are processed by storage device. Also, there are different kinds of storage interfaces such as SCSI, ATA, or NVMe. So these are different type of storage interfaces. And then in order to support these different interfaces, we need to have the device drivers. Okay. This device driver received the block-based command from operating system, and then based on the supported interfaces, then this block device drivers generate its own control signals to the, and then delivers this own control signals to the storage devices. Okay, so device drivers. So the high level is very simple. We just access the file based through this file system, or we can access the some block of the storage system directly. So it's based on the low level management functions. Also, the operating system supports the block level read, write, erase command. It's also very simple. So in the operating system view, the data inside of the storage system is like a block-based memory system, block-based memory. Okay, but this block-based command is translated into some, it's a specific interface command via based on the some different storage interfaces. And then when the storage devices receive this storage interface command, then storage device also translate this command to its own storage media access command. So actually the inside of these devices is very complex, but only the required interface commands are supported. So this different interface commands are also translated into very simple block-based command. So this is the abstraction. Okay. And also based on this abstraction, and the storage system is managed by operating system. Okay. Okay. So this, let's see the example of the IDE interface. It's a very old storage interface. It's called the IDE. So you can find some registers here. Is a control register. Then you can find the address here, and then you can find how the register can be controlled by some contents of this registers. Okay, so you can find the control register here, and the command line register, and the status register, and error registers. So this ID interface has its own address for the registers. Okay, so how can operating system control this ID storage device? So this is some code snippet of the device driver for ID storage device. So we can use the wait and ready command. So as we already mentioned, as we already saw, so there is the control register here. So with this ID wait ready command, it's a function. It's a function of the device driver. So the CPU reads the contents of this register file 1F7. Where is the 1F7? Here. So status register here. So CPU reads the content data from okay. So CPU reads this status register from ID storage device, and then wait until the device is ready. And then if the device is ready, then CPU generate request by writing some data to the control register of this ID storage device. Okay, so you can find ID wait ready function here. Is this function. You can find some specific command here, out B, out B, out B. So this is the programmed IO, PIO. So with this dedicated command, with the out B command, the operating system, that is actually the CPU, operating system write some specific command on this command registers here. You can find the low byte LB logical block address, mid byte, high byte here. So you can find that LB is written to this control register here. Okay, and then also the command is written to the register. So write command and the read command. The request is written to this control registers, and then if this command request is written to the control register, and then the data transfers can be done by this host processor and IO devices. Okay, based on some defined protocol. Okay, then we can usually use the DMA commands for this data transfer, and the data transfer is done, the interrupt is raised, and the interrupt is handled by CPU. Okay, that's how the IO devices are controlled. So that means, originally the hard disk drive or some storage device performance is very low. That means that the speed of this storage device is very slow. So usually conventionally the storage device is controlled by interrupt-based control. Okay. So till here I mentioned how until here I explain how the computer system or host system controls the IO devices or some storage devices using some control protocols or some control commands. So we learned how the computer systems are built based on some CPU and some memory bus and the GPU bus, and then some point-to-point IO communication network. Okay, so actually we learned how the IO devices are basically controlled by host computer system. Okay. So this is some basic knowledge on the operating system, and then how the IO devices are controlled. Okay. So then in the next class we will learn how the hard disk drives are controlled and how the hard disk drives are managed by operating system, and then also we will learn how hard disk drives are how hard disk drive works. Okay.